I think it's question number 4, right? The tank problem, the mixing problem. So in that problem, you have a tank, right? You have a tank and it contains m naught amount of sugar. At t equals 0, it contains m0 is equal to m naught and its volume is going to be equal to v naught, right? So this is the initial volume, v naught, right? So at this time, we are going to insert pure water into this tank at a rate of Qi, right? That means uh, Qi liters would enter into this tank within 1 minute, okay? And Q out amount of liquid would go out of the tank within 1 minute, right? And I have given that Qi is greater than Q naught. That condition is very important, right? Because if Qi equals Q naught, that means if input rate is equal to output rate, then the volume in the tank is going to be constant. Volume is not going to be changed, right? But since Qi is greater than Q naught, the volume is going to change, right? So in part A, I asked what is the rate of change of volume, right? So what is the rate of change of volume of this tank? So this is time 0 and at time t, this is at time t, input rate is Qi and output rate is Q naught and output concentration is C naught, right? So volume is Vt and sugar amount of at time t is empty, right? Because initially this tank contains m naught sugar amount, but we are going to dilute that. So dilute that amount, right? So the sugar amount is in this tank is going to decrease, right? Because we are inputting pure water, right? Okay. So what is the rate of change of volume? It is equal to Qi minus Q naught, right? So rate of change of volume is going to be equal to Qi minus Q naught. Both of them are constants, right? Qi minus Q naught. Then you can easily find Vt by solving this differential equation. You can use separable method, right? So how do I do that? dV is equal to Qi minus Q naught times dt. I would integrate both sides. dV is equal to Qi minus Q naught dt. So I would get V equals Qi minus Q naught T plus C. Okay. Then I would plug the initial condition. I know that at time equals 0, Vt is going to be equal to V naught. Okay. So then plug t equals 0. Then you would get V0 is equal to C. Okay. Because if you plug t equals 0, Qi minus Q naught times 0 would become 0. Right. So I know the initial condition. So V naught is going to be equal to V. Oh, right. So Vt is going to be equal to Qi minus Q naught T plus V naught, right? This is the volume of this tank at time t. Okay. Right. Did you get that idea? I did the same thing using numbers in the lectures, but for the exam I gave you algebra. Right. So after you find Vt, it's easy to find the expression for Mt, right? So what is the formula for dMt over dt? As we discussed in the class, the formula is going to be Qi Ci minus Q out C out. Ci is the concentration of the liquid that you are inputting this to this tank, and QO is the CO is the concentration of the liquid that would output from this tank. Okay. So what is Ci? What is Ci? You're inputting pure water, right? So what can you say about Ci? Ci equals 0, right? The concentration of the liquid that you are inputting is going to be equal to 0. So the first term would become 0, and this is equal to QO times CO. Okay. Right. So what is the output concentration at time t? So at time t, the volume is going to be empty. Sorry, mass is going to be empty and volume is going to be Vt, right? But we have the formula for Vt. Then plug that there. So I have this differential equation. Dm over dt is equal to minus Q naught m divided by V is minus Q naught m divided by V is going to be equal to Qi minus Q naught times T plus V naught. Okay, right. Then this is again a linear differential equation. Okay, so use integration factor method or separable method to solve this equation. Then you would be done, right? Use integration factor method or separable method. Right. I hope now you can have the idea. To simplify your computation, you can use some dummy variables. That means use something like this. Use A equals Qi minus Q naught. Then it's easy to simplify, right? Then what is the expression? Dm over dt is minus Q naught divided by AT plus Q naught times M. Right? I would suggest you to use separable method. That would be easy for this problem, right? Because you can easily separate M and T, right? You can take dt to your right hand side and M to your left hand side. Then you will be done, right? Okay. Any other difficult problems in the exam? So I would suggest you to try the exam on today, right? So if you get any trouble, please let me know on tomorrow. Then I can give you some hints, right? Because deadline is Friday. So if you can tell me that on tomorrow, then I can give you some hints, right? Okay. Right. So I would move into our discussion, right? About Laplace transforms. Yesterday I stopped from this point, right? I showed you how to find the Laplace transform of derivative, first derivative and second derivative. Actually, those two are the most important things for us, right? And we can, by using those two, we can find the Laplace transform of third derivative also, right? So again, I would go through them first, right? So formula is important. So we discussed that suppose you have some function and you know the Laplace transform of that function. Suppose you have simple ft, you know that its Laplace transform is going to be equal to fs. Okay, then what did you discuss? How to find the Laplace transform of the first derivative of this function. Okay, it is going to be equal to s times fs minus 0 minus f0 simple f0. Okay, so this is capital F, this is simple F, right? Right. Then we discussed the fact that Laplace transform of the second derivative is going to be equal to s square f s minus s times f dash 0. I have to go through the formula. S times f0 minus f dash 0. Okay. These two are very important, right? Okay. Any questions about these ideas that I discussed on yesterday? So I would put my focus to final value theorem. That is very important because suppose you have a system, right? So we are interested in the idea that what would happen to our system when time moves on, right? So that means because we would like to have some stability in our system, right? So if that is unstable, then system is going to collapse, right? Unstable means when time moves on, our amplitude of pressure, suppose you have some tank and you are measuring the pressure in this tank, right? Suppose with time, the pressure is going to increase exponentially. Then what is the end result? The tank is going to collapse, right? So we would like to have some stability in our systems. So we would be interested in what would happen to the system when time moves on, right? So I would uh, suppose you have some differential equation. Suppose you have some differential equation. Differential equation means you have some mathematical model, right? So suppose your differential equation is something like that. F of y. Okay. We are interested in limit t goes to infinity yt. That means we are interested in the idea of what would happen to our system when time moves on, right? When time goes to infinity, what would happen to our system? We would like to have some boundary to this value, right? This would be very important. When we are determining the stability of the system. Okay. So as I mentioned earlier, we would like to have some stability in our systems. Okay. Right. So by using final value theorem, we can easily find this limit. Okay. Final value theorem gives you some idea how to find this limit without finding yt, right? According to this definition, we need yt to find this limit, right? So final value theorem would give you a very good result, right? So if you use final value theorem, you do not need yt, right? It's enough to have the Laplace transform of yt. Okay, so that's why this result is very important. Understand that, right? So when you are learning a theorem, first try to understand why we are going to learn this. That's important, right? Okay. So final theorem. Right. Suppose you have some function. Suppose that ft is a function of exponential order defined on 0 infinity. Okay. Let the Laplace transform of ft be fs. Is we have some function ft that is defined on positive t, and you know the Laplace transform of ft. So Laplace transform of simple ft is going to be equal to capital F s. Okay, right. Then I would state the statement of final value theorem. So what does final value theorem says? Final value says limit t goes to, I think I have to go to the next line. Says limit t goes to infinity ft is going to be equal to limit s goes to 0 s times fs. Okay, that means we can find the limiting behavior of system by using its Laplace transform, right? This is going to be very important, right? I would show you an example. Right. Consider this example. Consider the differential equation given by y dash plus y is equal to 1, where y0 is equal to -2. Right? Find limit t goes to infinity y of t. Okay, as I mentioned earlier, this is some system, right? This is a differential equation. That means this is some physical phenomena, right? And that phenomena is governed by this equation, right? So, and as I mentioned earlier, we are interested in the limiting behavior of the system. What would happen to system when time goes on, right? So we would like to have some stability. We would like that this this is not to be infinity, right? If this is going to be infinity, that would be a problem. Suppose why it is pressure. Pressure is going to be infinity. That means pressure is getting bigger and bigger, right? Suppose why it is temperature. Temperature is getting bigger and bigger, right? So, right. So we'd like to have some stability of YT, right? So let's check whether it is going to be stable or not, right? Okay. So let's use final value theorem. So what does final value theorem say? Now you have system, and if you can find the Laplace transform of y, so I would take Laplace transform of y as capital Y, right? Let Laplace transform of yt be equal to capital Y s. Okay. To use final value theorem, we need the Laplace transform of y. That means we need ys. Okay, let's try to find ys. Can you give a try to find ys? By using the facts that I discussed on yesterday. Now you have differential equation, take Laplace transform in both sides. Okay. Can you give it a try to find ys? It's some problem in exam, that is the mixing problem. Okay. You can watch the video. Okay. Okay. And I introduced final value theorem. Okay. It says that limiting behavior is still this equation. Okay. If you have system and you need to find the limiting behavior of the system, so it is equal to use the given differential equation and try to find ys. Just consider the given differential equation, right? You are given that y dash plus y is equal to 1, right? So apply Laplace transform to both sides, right? So Laplace transform of y dash plus y is equal to Laplace transform of 1. Okay. So for left hand side, I'm going to use the linearity, right? So by the linearity, I can say that my left hand side is equal to Laplace transform of y dash, that is dy over dt, plus Laplace transform of y is equal to Laplace transform of y. Now let's use the equation that I introduced on yesterday. Right? I mentioned that Laplace transform of y is going to be equal to ys, capital Ys. Okay. So what is the Laplace transform of its derivative? By the formula that I introduced on yesterday, this is going to be equal to s times ys minus y0. And Laplace transform of y is equal to ys. And Laplace transform of 1 is going to be equal to 1 divided by s. Okay. Can you subject ys? Plug y0, right? I have given y0. Y0 is equal to -2. So you would get ys times s plus 1 minus y0 is -2 is equal to 1 divided by s. Okay. Then try to subject ys. Right. Right. So what would I get? Ys times s plus 1 plus 2 is equal to 1 divided by s. Right. Then I would take 2 to my right hand side. So ys times s plus 1 is going to be equal to 1 divided by s minus 2. Right. Then divide both sides by s plus 1. Then I would get ys is equal to 1 divided by s times s plus 1 minus 2 divided by s plus 1. Okay. Now the second term is okay, right? Try to find the partial fraction decomposition of the first term. 1 over s times s plus 1. Can you try to find the partial fraction decomposition of that? Actually, for this problem, it is not necessary because we need to find the final value or limit of yt. So I think without finding that limit also we can do this problem without finding the partial fraction decomposition, right? I'd show you that, right? So any questions up to this point? Any questions about finding ys? Let me know if you have any questions. No questions? Right. So what is our problem? Our problem is to find this limit, right? Limit when t goes to infinity. That means what would happen to our system when time moves on, right? That's the idea. Right. So now I'm going to apply final value theorem. Let's apply final value theorem. What does it say? It would say that limit t goes to infinity yt is equal to limit s goes to 0 s times ys. Okay. This is important. This is the statement of final value theorem. Right. Right. Okay. Now we know ys, right? Ys is 1 divided by s times s plus 1 minus 2 divided by s plus 1. Right. Now equals to infinity. Yt is equal to limit s goes to 0, s times ys. What is ys? Is 1 divided by s times s plus 1 minus 2 divided by s plus 1. Okay. Right. Let's multiply this expression by s. So what would we get? Limit s goes to 0. If you multiply the first term by s, you would get 1 divided by s plus 1. And if you multiply the second term by s, you would get 2s divided by s plus 1. So what can you say about the limit when s goes to 0? What would happen to this expression when s goes to 0? Yeah, it would be 1, right? Because second term would go to 0 when s goes to 0, right? Second term, that means this term would go to 0, right? This would go to 0 and the first term would become 1. So we would get 1. Okay. So we have some stability in this system, right? When t is getting bigger and bigger, yt would not grow up, right? It reaches 1. Okay. Right. Any questions so far? I'll do another one example. Consider differential equation given by y double dash plus y is equal to 2. Yeah, y0 is equal to, I would say, 0 and y dash 0 is equal to 1. Can you give a try to solve this problem? My problem is find the final value. That means find limit when t goes to infinity phi t. If you are doing electrical or mechanical engineering, I think you might have seen these things in control systems. Are there anyone doing electrical or mechanical? Have you done control theory?
Just a little, not very much. We don't go very deep into it.
Okay.
I think electrical goes further into it.
Yeah. Control theory and robotics, they usually use these things. I think for engineering students, after you graduate, there would be exam, right? If you, there's an exam that you have to write after you graduate.
Exactly, there's an exam. I don't think it's required in a sense, but it's
Not required, I think.
It gives you like, looks good on your resume. It's like an extra boost.
Okay. For that, I think you have to write an exam, and because the professor who taught this, he told that this Laplace transform is going to be very important part of that exam. Yeah.
It wasn't, and I don't know, some people saying that there is an exam that you do take, but it's not a part of this. It's like applying for a card or something. It's a certification that says, okay, you did all the classes, but did you apply it all on that one? It's like, when you leave high school, you gotta take that one big exam. And I think this one is more like it's just a boost. I'm not sure.
Okay. So apply the idea that we discussed on yesterday, right? We have the differential equation double dash plus y is equal to, take Laplace transform of yt by s. Okay, so let's apply Laplace transform to both sides. Y double dash plus Laplace transform of y is equal to 2 times Laplace transform of 1. Okay, right. Now you have the now you need the expression for Laplace transform of second derivative. So what is that expression? It is s square ys minus formula that I wrote minus s times y0 minus s times simple y0 minus y dash 0 equal to 2 times Laplace transform of 1, which is equal to 1 divided by s. Right? Can you try to find ys? Use the y0 and y dash 0 that I have given. I think I wrote the formula correctly. Yeah. Try to find ys and then apply final value theorem. And I extended the deadline of homework number 6. Right? If you need more time, you can try. I said that to Friday. Right, so y0 is 0, y dash 0 is 1. So I would get square ys minus y dash 0, that is 1, equal to 2 divided by s. That's what I'm getting. Then I would take 1 to my right hand side. Divided by s plus 1. Then I would divide both sides by s square. So ys is going to be equal to 2 times s to the power 3 plus 1 times s to the power 2, right? Right. So what can you say about its stability? So what can you say about, let's apply final value theorem. So by the final value theorem, by the final value theorem, we have limit t goes to infinity by t is equal to limit s goes to 0 s times ys. Okay. Right. So what would be your answer? You would get limit s goes to 0 s times 2 divided by s to the power 3 plus 1 divided by s to the power 2. Okay. 2 divided by s to the power 2 plus 1 divided by s. Right. So what can you say about the final answer? You have s in your denominator and s would go to 0. So what can you say about your final answer? Infinity, right? Because denominator would go to 0, so would get infinity. So this is an example for unstable system. Right. Any questions about that? Right. So let's discuss another one. Equation given by dy over dt plus 2y is equal to sine omega t with y0 is equal to 1. right? Find. It's instead of omega, I would use 2, right? Find limit t goes to infinity. Again, use the final value theorem. Right? So the Laplace transform of sin is the same technique that I use. First apply Laplace transform to both sides, use linearity, and find ys, then use the final value theorem. Okay. For this problem, I would like to have the answers from you. Right. Take your time and try to do this. Right. Yeah, yeah. Sure. Limit is 0 s times ys. Let's apply Laplace transform to both sides, right? So what should you get after that? Laplace transform of dy over dt plus 2y is equal to Laplace transform of sine of 2t. Okay. And then use the linearity. This can be written as Laplace transform of dy over dt plus 2 times Laplace transform of y. I used the linearity. And what is the Laplace transform of sine 2t? It's 2 divided by square plus 2 square. Okay. Right. So let's simplify the left hand side. We know that Laplace transform of simple y is ys. So this is going to be s times ys minus simple y 0 by the formula that I did on yesterday. Plus 2 times Laplace transform of y is ys is equal to 2 divided by s square plus 4. Okay. Right. So I would get s times ys minus y0. Y0 is 1 plus 2 times ys equal to 2 divided by s square plus 4. Okay. Then what would I get? S plus 2 times ys. I would take negative 1 to my right hand side. So get 2 divided by s square plus 4 plus 1. Okay. Then I would divide both sides by s plus 2. Then what would I get? Ys is equal to 2 divided by s plus 2 times s square plus 4 plus 1 divided by s plus 2. Okay. Right. Now we can find the limiting value of yt. Limit t goes to infinity, yt is equal to limit s goes to 0, s times capital Ys by the final value theorem. Okay. Now we would plug ys equals to 0, s times ys. Ys is 2 divided by s plus 2 square plus 4 plus 1 divided by s plus 2. What can you say about your final answer? 0, right? Because if you multiply by s and if you plug 0, you would get 0. Right. Okay. Again, we have a stable model, right? Because when time goes on, system would not collapse. Right. In the second example, we saw an example for collapsing system. Right. I hope now it's you have no questions related to final value theorem, right? So next I would move into next section, that's translation theorems. We would take a small break and continue. Okay, we would continue. Right, so next I would start translation theorems. First translation theorem. These translation theorems are also very important, right? So suppose you have function. Suppose we have a function ft of exponential order defined on 0 to infinity. Okay. Let the Laplace transform of ft be fs. Right. That means Laplace transform of ft is going to be capital F. Okay. So this theorem says that if you the multiplication by exponential in the time domain would result in the translation in Laplace domain, right? I would write that down. Then Laplace transform of, suppose you are going to multiply ft by e to the at. Okay. Then in the Laplace domain, you would get a translation fs minus a. Fs is the Laplace transform of function simple f, and if s minus a is some translation of capital F. Right? I hope you're familiar with the term translation. That means you would translate the graph. Right? You are not going to change fs. Right? For example, suppose fs is something like this. Suppose fs is something like this. Right? And suppose a is somewhere here. This is fs. Right? So what would happen? What can you say about fs minus a? You have to translate this by a units. So fs minus a would be was this would start from here. Now this function is going to start at a. You're going to translate this graph by a units. Okay. The translation. And then I would explain what is going to happen in time domain and S domain or Laplace domain, right? Suppose you have some function in time domain. Right. So Theorem. Suppose I have some function. Let's consider ut. Right. Now you are familiar with what is ut, right? Ut is a function that is 1 when t is positive and 0 when t is negative. Okay. Right. Suppose you have function ut. This is your t domain. And this is your function ut. Right? And suppose you are going to multiply ut by e to the at. Okay. Then what would you get? Then you would get e to the at. Suppose a is positive. because based on A, the shape of the graph is going to change, right? So what is the shape of U to the 80? Look like this. Okay. Because ut is 1 and 1 would be multiplied by e to the 80. So you would get e to the 80, right? This point is 1, right? This is what would happen in the time domain, right? So the time domain, the thing would become complicated, right? I had ut, and if I multiply ut, because it's ut, I would get this kind of nice shape. Suppose instead of ut, I selected t square or something. Then after multiplied by e to the 80, I would get t square times e to the 80. So the graph would be going to change, right? But nice thing would happen in the Laplace domain. This is what would happen in the time domain, right? I had some function and I multiplied that function by exponential, and this is the result in time domain. So let's consider the S domain or Laplace domain, and let's consider what would happen in S domain. Right. In the S domain, what is the Laplace transform of 1 divided ut? S domain means I'm going to take Laplace transform of these two. What is the Laplace transform of ut? It is 1 over s, right? So what is the graph of 1 over s? Laplace transform of ut with s. So the shape of 1 over s is going to be like this. Okay, this is 1 over s, right? This is the Laplace transform of t, which is equal to 1 over s. Now, what can you say about the Laplace transform of e to the at times ut? Laplace transform of ut is 1 over s. So by the previous theorem, Laplace, if you multiply ut by e to the at, what would become to its Laplace transform? It would get translated by a. That means this is equal to 1 divided by s minus a. Okay, because if s is 1 over s, and if you replace s by s minus a, you would get 1 divided by s minus a, right? So what would happen to your graph? In the first graph, you have vertical asymptote at 0, right? Now you are going to get the vertical asymptote at a. Okay. So instead of having vertical asymptote at 0, now you are going to get some translation, right? So everything would be nice in Laplace domain, right? But it is not nice in T domain, right? When you're multiplying by exponential function, it is not going to be nice, right? But in the Laplace domain, we only get the translation. So this is very useful theorem, right? Try to take the idea, right? What is going to happen, right? And if you are doing electrical or mechanical, this idea would be important in signals and systems. If you do Fourier transform, same ideas would be repeated, right? Right. Let's do some examples. Rather than examples, I need you to try understand the idea, what is going on, right? Because examples is about plug-in numbers, right? So again, I would write down theorem, first translation theorem. It would say that if you multiply your function by e to the at, you would get your Laplace transform would be translated by a units. Okay. Example number 1 is Find the Laplace transform of f t equals e to the minus 2t cosine 3t. Right? Use the first translation theorem. Right? Now I have multiplied ft by e to the minus 2t. Instead of considering e to the minus 2t times cosine 3t, first try to figure out what is the Laplace transform of cosine 3t. So in this case, your function is cosine 3t, and you are multiplying that by e to the minus 2t, right? And you know the Laplace transform of cosine 3t, right? Then you can figure that out. What would happen if you multiply that by e to the minus 2t? Okay. I would do this one. So let's see, right? What is the Laplace transform of cosine 3t? That is s divided by s square plus 3 square, which is equal to s divided by s square plus 9. Okay. Right. So then I need Laplace transform of e to the minus 2t cosine 3t. So what would happen to the Laplace transform of cosine 3t? It would be translated by minus 2 units. Okay. So replace s by s minus minus 2. Okay. Is equal to s plus 2 divided by s plus 2 square plus 9. Okay. Is that clear? So you had a function and you know the Laplace transform of this function is cosine 3t. Okay. And you are going to multiply that function by the exponential. Then the Laplace transform of cosine 3t would be translated. Okay. So the simple way of remembering this is multiplication by exponential in time domain would result in translation in Laplace domain. Okay. I would try to illustrate this graphical. Let's be first try to finish this. Finish writing this. Then I draw these two graphs in different. Okay. So first I would illustrate what would happen in the time domain, right? So first consider ft equals cosine 3t. This is cosine 3t, right? Then on the same diagram, I would multiply this by e to the minus 2t, right? So I will call that function as gt. Gt equals, I would multiply that by e to the minus 2t and cosine 3t. Okay. Now you can see everything would get complicated, right? After you multiplying by e to the minus 2t. Okay. Graph is going to change a lot, right? So this is what is going to happen in time domain, right? So the red colored graph is the cosine 3t, and after I multiply that by e to the minus 2t, you would get some oscillating function like this. Right? Let's look at what would happen in the Laplace domain. Right. So what is the Laplace transform of cosine 3t? I would call that as G. S is going to be equal to S divided by S square plus 3 square divided by S square plus 3 square. Okay, this is what would you get, right? So then what would happen to the Laplace transform of cosine 3t if you multiply that by e to the minus 2t? So we would get this equal to plus 2 plus 2 divided by plus 2 plus 9. Okay, you can see the translation, right? So purple colored one is my original graph, and the green colored one is my original graph, and the other one is my translated graph, right? Because if you consider GS at S equals 0, you get 0. And if you consider Fs at S equals minus 2, you would get 0, right? So it has been translated by 2 units. Okay. So in the Laplace domain, everything would be nice, right? Continue again. My next example. Find the inverse Laplace transform of 2 divided by S plus 2 square plus 1. How do you find this? First, apply linearity. So then you would get this is equal to 2 times inverse Laplace of 1 divided by S plus 2 square plus 1. Okay. This is kind of tricky because you have to connect the first translation theorem. Okay, right. You can see that s plus 2 to the power 2 is appearing. Okay, so our target is to find the inverse Laplace transform of this function. So, but what can you say about the inverse Laplace transform of this function? 1 divided by s square plus 1? What can you say about this one?
Sine.
It's sine, right? Sine t. Okay, because instead of omega we have 1. So this is equal to sine t. Okay, right. So how to get 1 divided by s plus 2 square plus 1 out of this expression? What do you have to do? Yeah. 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 Instead of s, you have to substitute s plus 2. S minus minus 2. Okay. Right. So what would you have to do in the time domain to to resolve that? To have this expression? What do you have to do in the time domain? You need s plus 2 in your denominator. To get that, what is the thing that you have to do in the time domain? You need to multiply sine t by some exponential, right? Because we know that Laplace transform of sine t is equal to 1 divided by s square plus 1. Okay, because inverse Laplace transform of 1 divided by s square plus 1 is sine t, and Laplace of sine t is 1 divided by s square plus 1. So what is the Laplace of e to the minus 2t sine t? By the first translation theorem, when you are multiplying by exponential, what would happen to your Laplace transform? That would be translated by, in this case, minus 2 units. So you would get 1 divided by s minus minus 2 square plus 1. Okay. So you would get s divided by s plus 2 square plus 1. Is that clear? Right. So what is the inverse Laplace transform of this function? Then it is going to be e to the minus 2t times sine t. Okay. So inverse Laplace of 1 divided by s plus 2 square plus 1 is equal to e to the minus 2t sine of t ut, because this is valid for t greater than or equal to 0. Okay. This would give us the answer, right? This was our goal. Right. Any questions about that? So you have to connect first translation theorem. Okay. So that would allow us to find the inverse Laplace transforms of this kind of complicated functions. Okay. We cannot directly write the inverse Laplace of 1 divided by s plus 2 square plus 1, but we know how to write the inverse Laplace of 1 divided by s square plus 1. Right. We are using that fact to find the inverse Laplace transform of the given function. Okay. Right. Let's move into another example. We find inverse Laplace transform of 2 divided by s square plus 4s plus 5. In this problem, use the completing square method in your denominator. Right. First, you can use the linearity and take the 2 out. Right. Right. So what is s square plus 4s plus 5? I'm going to apply completing square method. So you can write s square plus 4s plus 5 in this way. S plus 2 to the power 2 plus 5 minus 4, that is 1. Okay. I would get the same thing, right? Right. Now again, you can see that s has been replaced by s plus 2, right? So let's try to connect the idea of first translation theorem, right? So instead of taking inverse Laplace transform of s plus 2 square plus 1, so what can you say about inverse Laplace transform of 1 divided by s square plus 1 is sin t, right? Okay. Right. So by this, what can you say about inverse Laplace transform of this function? The red colored function. You need to multiply that by e to the minus 2t. Okay, because it has been translated by minus 2. Okay, so Laplace inverse of 1 divided by s plus 2 square plus 1 is equal to e to the minus 2t sine of t. Okay, right. So my target is to find the Laplace inverse of 2 divided by s square plus 4s plus 5, which is equal to 2 times Laplace inverse of 1 divided by s square plus 4s plus 5. I found the value that is equal to 2 times e to the minus 2t times sine t. And I am writing ut also because this is valid when t is positive. Any questions? Any questions? Again, remember, is the idea. Translation in Laplace domain results in multiplication by an exponential in time domain. This is what first translation theorem says. Okay. It's the main idea behind first translation theorem. Translation in Laplace domain would result in multiplication by an exponential in time domain and vice versa, right? That means multiplication by exponential in time domain would result in translation in Laplace domain. Right? Right. Right. Next problem is inverse Laplace of 2 divided by s square plus 4s plus 3. Right. Can you give a try for this problem? For this, you would need the Laplace transform of hyperbolic state. Laplace transform of hyperbolic sine is going to be equal to 1 divided by t square minus 1. In general, Laplace of hyperbolic sine omega t is equal to omega divided by t square minus omega square. Right. Use this idea and use the completing square method in the denominator. Right. Again, I would apply linearity. Inverse 1 divided by. Then I would complete this square in my denominator. So I would get s plus 2 square plus 3 minus 2 square equal to 2 times Laplace inverse of 1 divided by s plus 2 square minus 1. Okay. Equal to L inverse 1 divided by s minus 2 square minus 1 square. Okay. Right. So if I do not have this negative 2 here, then I know it's inverse. Or it should be right. So it should be s square, right? So what is the inverse Laplace of 1 divided by s square minus 1? It is hyperbolic sine. Okay. Now s has been replaced by s plus 2 or s minus minus 2. Okay. So what is the Laplace inverse Laplace of this function? E to the minus 2t hyperbolic sine t. Is that clear? Original function was s square minus 1. It has been translated by minus 2. That means that would result in multiplication by exponential in time domain. Okay. Is it clear for you? First translation theorem. Okay. So I'm going to stop from this example because the next I would continue on tomorrow and go through the exam. And if you have any questions, please let me know on tomorrow.